Okay, welcome back. And what we were talking about previously was how the computer works, and we came up with this kind of diagram here that has memory cells, and the memory cells can each just store a simple number, 0 to range 255, no fractions, just whole numbers. And then we have the processor, which is really just another collection of simple circuits that can take numbers and manipulate them in one of a set of simple ways: adding, subtracting, multiplying, dividing, moving, comparing. And then we had something that connected that circuit to these circuits. That's the motherboard system buses that are on that board, basically just wires that connect them. And then there are these little latches. Now, all of the peripherals, no matter which kind it is, keyboard, mouse, hard drive, network card, graphics card, sound, everything that you can think of just connects to special memory boxes that have kind of two ways that numbers can get in or out. So for example, the keyboard, you press the letter A certain number shows up in this box, and the CPU, to see what key was pressed, has to go to that box and access it, and then pull it into a register to make a decision about what happened there. So relatively simple, easy to understand. Every computer system, no matter how big or small, works this way. Now, a couple questions we had last time. Where does the program come from? And I'm going to tell you that the diagram we have here is how every computer system works, and we don't really need to add anything to that. So where does the program come from? In other words, how does the program get its instructions into the CPU? And the answer is actually right in front of us. There's only one thing that connects to the CPU, and notice that's these system buses that connect to memory. So the only way that the place of the program can get into the CPU is it has to be in memory. So the program actually lives in memory. And actually, since the memory can only store numbers, that means that the program itself is represented as codes or encoded as numbers, like we see down here: add, subtract, multiply, divide. Those are really just numbers that represent each of those instructions like that. And we'll see that here in just a second. I'll actually bring up something and we can look at that, and I can prove to you that that's really what's going on in there. But looking at that, this add, subtract, multiply, divide, move, think about those as just having a number. Like, let's say the add is instruction 56 and subtract is instruction 82. And those aren't really correct. I just made those up. But there's just an encoding system that says this number means this action. And how does the CPU get that instruction? Well, it pulls the instruction out of memory and stores it in a special register that we don't have drawn here, called the instruction register, usually, IR. It pulls that instruction into there and stores it, and then that tells it what to do. Do I then go get something else and pull it into a register? Do I add this to that to get the result? So the answer to this first question, where does the program come from? It's stored in memory. Now, how does it get into memory? Well, it can get into memory by being loaded from the hard drive with a special program that then says go to the hard drive and tell it I want to access this file, and load up all these locations in memory to do that. But the only place a program can be executed from is it has to be loaded in memory. Now, how does it get started and get the first program in memory? That's a little more complicated than what we want to do here now, but there's no other things we need to add. The answer is the CPU, when it turns on, it goes to a very specific place in memory, and there's a program there that it runs, and that program then goes to the hard drive and loads a special small program in there, then goes back to the hard drive and loads a bigger program into memory, and then the CPU starts running that program. And that's kind of the boot process. When you turn your computer on and you see it do kind of a memory test thing, or it has a little logo screen, a starting up screen, all of that is from the CPU going to a certain address in memory and loading up whatever program it finds there, which loads up a bigger program, which loads up a bootloader for Windows, and then that loads Windows into memory and it starts running Windows, and then that loads other things. But it's really nothing else that's not in this diagram here is necessary to do that. Okay, now the second question, why the 0 to 255 range? And that turns out, for each memory cell, 0 to 255, that turns out to be something that we're going to answer now. And that turns out to be how those memory cells store the information. So let's move on to this next page here. And I believe we're on page 4, so let me go and write this up here in the corner. So this is answering y 0 through 255 in each memory cell. And the answer to that is the way that the computer remembers things is actually also really simple. The way that it keeps track of those numbers or remembers those numbers is actually really simple. And the way that that is that the memory in a computer system is essentially composed of, you can think of it as like a bank of switches. And the switches can either be off or they can be on. And so it turns out that each memory cell, as it's stored in memory, so here's a memory cell, let's say this is the one storing the number 0 that's at the top. But really, what that is, it's not the number 0 stored in there, it's just a bank of switches. And so here's a bank of each memory cell, and let's divide that up into 8 switches. And each switch of that 8, 1, 2, 3, 4, 5, 6, 7, 8, can either be off or it can be on. And essentially what this is saying is if all of these are off, so this is 8 switches, and each one can be either off or they can be on. And to simplify things so we don't have to write off and on, the way that we tend to represent that in computing is off would be a 0 and on would be a 1. So really simple, it's just, but really behind the scenes, these are just switches. And technically in a modern computer system, these are transistors, not physical switches like a light switch, but a little transistor that's either turned off or on. And a transistor is essentially like a electrically controlled switch. So if you turn it off, its output can feed or doesn't feed back to itself and keep it on. If you turn it on, the output goes back to the input and kind of latches it in the on position. So the idea is you turn it on, it stays on. You turn it off, it stays off. Just like a light switch on the wall. Kind of snaps into its state and stays there. So really the number 0 is just all of these switches turned off. Like that. Which, if there's only 8 switches, if I turn just one of them on, like that one there, that would be the number 1. If I turn this one on and that one off, that would be the number 2. Number 3 would be both this one and this one on. The number, if you follow that logic all the way through the all of the possible switch patterns, the largest number I could ever get with 8 switches would be all of them turned on. So that would give us, that's where that 255 comes from. So here's a memory cell holding the number 255, but really what that is this bank of 8 switches. So there's my 8 switches, and each one has a 1 in it. So all of them on, so all of them off is 0. And here, all of them on is 255. Okay, so that's essentially how that's storing numbers. And I'm going to go one step further in explaining this. And the cool thing is that if you think about this, these are just, each of the positions in this are really just places, just like you would have a number in decimal. But since there are only 2 possibilities, 0 and 1, this is a binary or a system called binary. So in other words, each of the memory cells uses binary instead of decimal and notice binary, nary is numbers, and bi is 2, so 2 numbers, 0 and 1. That's why they're called binary numbers. There's only 0 and 1 are the only digits we're allowed to have. We're decimal, we're allowed to have 10 different settings for each of the things. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we wrap back around to 0. The same thing works here, except that we're only allowed 0 and then 1, and then we have to roll back to 0 again. Now, because this is a number system, just like decimal, So we're up to page 5 here. All right, so let's start off. So this is kind of under the category of binary numbers. But before we do that, let's look at decimal first. So if I have a number like 124, now each of those numbers in decimal has a place value. So if we think about that, there's a place value, there's a place value, there's a place value. So the one all the way at the end, that's the ones place. So this means 4 times 1. And then this one is the tens place. So that means 2 times 10. And this is the hundreds place. So that means, in this case, there's a 1 there. So this is 1 times 100. And notice that you can kind of hear those place values when you read out that number, 124. So 100, 2 times 10 is 20, 120, and then 4 times 1 is 4, so 124. And you can kind of see that come out in those when you read that number. So each number has a place value, and notice that to go from one place to the next place, it just multiplies the previous one by 10. So this one is the ones place. 1 times 10 is 10. 10 times 10 is 100. The next place will be 1,000. 10 times 100 is 1,000. Next one will be 10,000, 100,000, million, and so forth. As we add additional places, we just multiply the previous 1 times 10. So in other words, this is the ones place. This is the tens place. That's the hundreds place, and so forth, going across there. Now, binary numbers in contrast to that, work the same way. But in our case, as we've talked about, we've got 8 switches. So there's 4, 5, 6, 7, 8. So there's my 8 switches. And so in this case, each of those has its own place value. But so this is still the ones place, just like we had over there. So this is still 1. But now this is not the tens place now, because we don't have 10 digits. It's not base 10. Decimal's base 10. Binary is base 2. So we only have 2 things. So 0, 1. And then so this, rather than the ones place, is the twos place. And the next one after that is going to be the fours place. And the next one after that is going to be the eights place. And then 16, and then 32, and then 64, and then 128. And you might see the pattern here that just like this one multiplies the previous place value by 10 to get to the next one, by 10 to get to that next one. This one, because it's not base 10, it's base 2. And let's go and write that over here. So decimal is base 10. Binary is base 2. I'll go ahead and write it down here. Base 2. But because of that, each of these place values that we have here multiplies the previous 1 times 2. So we always start with 1, but rather than 1 times 10 like we did over here, we do 1 times 2 gives us 2. Then 2 times 2 gives us 4. 4 times 2 gives us 8. 8 times 2 gives us 16. 16 times 2 gives us 32. 32 times 2 gives us 64. 64 times 2 gives us 128. And there's my 8 switches. Now, how do we represent a number in here? Well, let's put a number in there. And then let's see if we can figure out what number it is. So I'm going to go ahead and say, let's put it 0. And let's do 1, 1. Let's do 1. Let's see. Let's do 1, 0, 1, 0. All right, so let's do that. So that's the pattern of switches, 0, 1, 1, 1, 1, 0, 1, 0. Now, essentially what that means is just like we had our place values over here, 100 plus 2 times 10 plus 4 times that. The same thing is true here. So we have 0 times 128, which is 0, but then we have 1 times 64, which is 64. So this is essentially saying we have a 64 from there plus a 32. So plus 32 plus a 16 plus an 8. And then there's no 0 there, so plus a 2. And that's what number this is. So let's go ahead and add all of those up. So to add all of those up, that would give us what number that's representing in decimal. So 64 plus 32. Let's just stack these up and add them like we would in grade school. So 64, 32, 16, 8, and 2. All right, so we're just going to add all those. All right, so let's add all those up. So here we have 8 plus 2 is 10, 6 plus 4 is 10, so we're now at 20 with 2 left over, so 22. So 4 plus, we could go down the line here, 4 plus 2 is 6, plus 6 is another, is 12, plus 8 is now 12 plus 8 is 20, plus 2, so this is 22. So we're going to put the 2 down here, and then up here, we're going to carry the 1, or the 2, because that was 22. And now we have 6 plus 3 plus 1 plus 2. So 6 plus 3 is 9, plus 1 is 10, plus 2 more is 12. So 122. So we had 122 over here, looks like this inside of the memory. So 122 is essentially no 128s, 164, 132, 116, that, or 0 of those, 1 of those. So 64 plus 32 plus 16 plus 8 plus 2 is 122. So when you store 122 inside of the computer, it looks like 0, 1, 1, 1, 1, 0, 1, 0, which is really doesn't even look like ones and zeros. It's just a switch that's off. That one's on, that one's on, that one's on, that one's on, that one's off, that one's on, that one's off. That's the pattern that it would look like, but to us, that could represent a 122. Now, a couple quick things here. What if I wanted to have that 124 in there? Notice that would be pretty easy to store. We just need to have 2 more than we have now. So if I were to add this 4 and take away 2, that would be 2 more than I have now. So if I move that 1 over there and put that 0 over there, I would now have the same number in both methods of storing that. All right, so a quick thing to note here is how do we convert from binary to decimal? Well, we just did it there, but let's look at that a little more carefully here. So this is 6, and we're going to kind of finish up on this example. Convert from binary to decimal. All right, so let's take a binary number and see if we can figure out how to do this. So I'm going to take an 8-bit binary number. Let's do 1, 0, 0, 1, 1, 0, 1, 0. So there's my 8 places. Let me go ahead and mark those. So I've got my 8 places here that we're going to be marking, or that we marked. So there's my 8 bits that make up that one memory cell. All right, so how do I convert that? Well, it's really easy. We just write the place values above those and then add up any of them that have a 1 and ignore any of them that have a 0. So in other words, this was the 1's place, that's the 2's place, 4, 8. And it's easy to reconstruct this because you just start with 1, they double every time. 8 times 2 is 16. 16 times 2 is 32. 64. 128. So if I look at the ones that have a 1 in there, I've got 128. So down below this, Let's go ahead and write those. So we have 128 plus a 16 plus an 8 plus a 2. So in other words, the 128 came from there, the 16 came from there, the 8 came from there, and the 2 came from there, and we basically just add these up. So 128 plus 16 plus 8 plus 2, we can just add these up just like in grade school. So 8 plus 8 is 16, 17, 18, plus another 6. Let's see, we're at 18. So we're at what, 24 here? Yeah, so 8, that's an 8, so 8, that's 24. So 4 carry the 2. So 2 plus 2 is 4, plus 1 is 5. Nothing gets carried there, so 154. So that's what a 154 value, let me make that a little more clear, that's a 5. 154 looks like that in memory. Now, you can do that with any binary number, and it turns out that the range of possible different numbers you get would be 0, where all of these are all zeros. Fill in that with all zeros, you get the number 0, because 0, 128 plus 0, 64. If they're all 0, nothing gets added up, you end up with 0. Now, the high end of that, the biggest number you could ever get, is with all of them ones, and it turns out that a 128 plus a 64 plus a 32 plus a 16 plus 8 plus 4 plus 2 plus 1, that adds up to 255. That's the biggest number that you could store in there is 255. So the reason for that range, this answers the question of why the range 0 to 255, is we basically just have switches inside of there. A bank of 8 switches makes 1 byte of memory, which is considered kind of one logical grouping of memory. And that is 1 cell of memory, and that's the size number it can store. Now, there are a couple other things that we were going to answer that we had questions about. Let's go and just quickly answer those. And that is, well, what about other things like text and images and sounds? It turns out that those are just stored as in memory as numbers as well. So for example, text. There's a code that associates characters with each of the kind of with a number. So for example, that code is called the ASCII code. But it turns out that the number 65 decimal is a capital A. It turns out 66 is B, 67 is C. But every character that you would see representing something is really just stored as a bit pattern or a set of numbers. And we'll look at that code a little later on. Images are just stored as the pixels that make up the image data, like a bitmap just stores, here's the red component, the green component, and the blue component of this thing. And there are some more clever ways of storing those that are compressed, like PNG and JPEG images, but really, ultimately, those get decompressed into just numbers that are associated with the pixel values, the individual dot values for the red, green, and blue components that make up that image. What about sounds? Sounds are just stored as numbers as well. The number representing, like here, 154, a point on a waveform that would make that sound happen when it gets pushed out to a speaker. What about bigger numbers? Well, if we can only store numbers 0 to 255 in 1 byte or 1 memory cell, you just use 2 memory cells together, and then instead of 8 switches, we have 16 switches. And it turns out if we're using those as a block of 16 rather than a block of 8, we can store numbers in a much bigger range than 0 to 255. So rather than just with 8, we have 255. If I had 16, like twice the width here in memory, I could store a number up to 65,535 because it doubles every time. So 128, the next place would be 256, 512, 1024, 2048, 4096, 8192, and so forth. So you can just store bigger numbers by using blocks of memory or memory cells together to store those. What about fractions? Well, that's a little more complicated, but it still uses a memory cells together to store those fractions. And if they're stored as what are called floating point values, then it basically has a bit pattern, and part of it tells you where the decimal place goes in that. But it's really the same as like a binary number that has a decimal place placed somewhere in it, And notice that the binary numbers work with fractions, because if this was the ones place, you could have the 1/2, the 1/4, the 1/8, the 1/16. And so you just have this fractional part over here, but it's the same as decimal, it's just base 2 rather than base 10. And a question that always comes up is, like, well, why do computers use base 2? And why do humans use base 10? And that's actually a really interesting question. And the reason computers use base 2 is because it's really easy to make an electronic or even a mechanical switch that's either turned off or it's turned on. So that's an easy thing to make. Where having something that's like partway turned on or is a more complicated to design and build, but having a switch that either it's on or it's off is easy to make. And so that's why computers are built that way. But there's nothing magical about this kind of number system. There's nothing special about it. It works just like base 10 does, as we saw back on this previous page over here. Decimal numbers work the same way. They're just base 10 instead of base 2 like we have over here. So the question is, why did humans use base 10? Like why do we as humans use this like base 10 numbering system? Why is that more natural to us? Well, it's more natural for computers to use base 2 because it's easy to build switches that turn off and turn on. But why do humans use base 10? And I've had people before, they'll say, well, it's just easier. And the question is like, well, what makes it easier? Why is that easier for us? And they're like, well, it's just naturally easier. But it really isn't. It's the only reason that we use base 10 and have historically used base 10 is because we happened to have evolved with 10 fingers. And so we have 10 fingers, so we tend to see the world around us in groups of things that we can count on our fingers. So we use base 10 because we have this kind of built-in way of thinking about the world as counting up to 10 before we have to use somebody else's fingers. And you can kind of see that in the number system here, that we have a digit that can represent every possible configuration that we have on our fingers, and we run out of fingers, we have to roll over to use another digit with somebody else's fingers. So it's the only reason that base 10 is easier for us or seems more natural is we have been taught that, we grew up learning that. There's nothing magical about that. So in other words, base 2 works exactly like base 10. If you know how to do arithmetic and know how to do counting in base 10, you can do it in base 2 and in binary as well. All right, one final thing. Let's go back to that picture of the computer that we had for just a second. If that's all that it's doing, so back on page 3 here, if that's all that it's doing is storing these patterns of switches inside of memory and then being able to move them into this CPU and then perform a really simple operation that we could do ourselves, if that's all that it's doing, then why do we use computers? What makes them powerful? Because we could just play this game on paper and write numbers down and pick them up and add one to another one and write it down in another spot. What makes the computer a powerful kind of world-changing invention like we talked about earlier? And the answer to that is that computer systems are powerful for 2 reasons. The first reason is that on this diagram we have here, we have a relatively small number of boxes written. But inside of a computer system like your laptop or a desktop computer, like a gaming computer, there are more than just what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 memory cells drawn here. It has a lot more than that. In fact, that there are billions of memory cells inside of your computer that can each store a number. So there's a lot of places there to store complicated data. There are a lot of places to store that stuff. And because we can use those same memory cells to store numbers, but also use those numbers to represent the program itself that does operations, and use the numbers themselves to store parts of text or images or sounds, we can put a lot of different information into those really simple memory boxes. So that's the first thing, is there's a lot of memory boxes inside of a typical computer thing. The second thing that makes them powerful is that this processor can pull things out of that memory and perform one of these simple operations and then put something back into memory at an incredibly fast rate. And so, and it does so without errors. So it does that without having problems or making mistakes for the most time, unless there's a cosmic ray that hits it or radiation, some other sort of radiation that interferes with it. It will flawlessly pull data out of memory, perform one of these simple operations, and put it back in there. But there's nothing magical about the computer system. There's nothing special about it. There's nothing smart about it. It's not really thinking. It's just blindly pulling an instruction from memory, doing what that instruction told it to do, one of these simple things. And then once that instruction is done, goes to memory and gets the next one, pulls it into the processor, carries out what operation it told it to do, and then gets the next one. It just does that as fast as it can. And when we say that that's fast, that's kind of on human scale, that's hard to comprehend how incredibly fast that is. But we're talking like modern systems that run at like, I don't know, like 4 gigahertz. That's like 4 billion of these operations per second that it can perform. And modern CPUs actually have more than one core inside of them. So in other words, you think of a CPU carrying out one of these instructions, like a modern CPU with 8 cores inside of it would have 8 units that can all be kind of overlapping these operations. So it could pull in a block of instructions, have one adding while the other one is subtracting, while the other one is comparing, and it can kind of, or it could be running part of one program while also in one core, while also running part of a different program in another core. But it's incredibly fast and powerful to be able to put even simple instructions together at that kind of incredibly high rate. And that's where the power comes from. So it's not magical. It's not thinking. It's not really doing anything other than really simple operations. And it doesn't even know what it's doing. It doesn't know that it's reading from the keyboard. It doesn't know that it's writing things to a graphics card to the screen. It just is doing what it's told with these simple instructions. Now, that being said, next class I'm going to take a little bit of time and look at this a little bit further. I also want to look at how do we convert these numbers going the other way. In other words, how do I start with the decimal and create the binary? We know how to do binary to decimal. So next time we're going to look at decimal to binary. And then we're going to look at one other numbering system that can make it easier to do stuff with computers. And then we're going to dig into some actual programming next time. Now, the programming that we're going to do in here, it's not going to be at this low level that we're talking about here with the processor doing these things. Although we could program a computer at that level. You'll actually have some classes where you do some lower level stuff like this later on in your career, in your education. But we're going to use a tool that makes it, which is really just another program that makes it easy for us to control this thing in a more human-like way. So we're going to use what's called a high-level programming language to program this. So don't get scared off by this stuff. Just know that it's useful to know that this is how a computer works. Just memory, a CPU, wires that connect it together, peripherals that connect to memory. When you hit a key on the keyboard, it changes something in memory. The CPU can then have a program that reads that, makes the program do something different based on what you said because it has a comparison, and then produces a result that shows up on the screen. In next class, I will dig in and look at some of these conversions. We'll look at a different numbering system called hexadecimal, which makes it a little bit easier to convert back and forth and keep track of that. I will also prove to you that this is really how the computer system works. That it's not like that diagram we had earlier, that dumb thing with this thing. It's not like this. This is actually a useful diagram that is really how the computer system works. And I'm going to prove to you that that's what programs look like in memory in the CPU. And we're going to learn those other things. And then we're going to get started on programming in a high-level programming language, which is where the real fun should start. So let's go ahead and stop there for today. And let me... All right, so we went through that. What is a computer? How does it work? And then how do we get it to do what we want it to do? Well, we're going to look at that next class. But that's it for today. Everybody stay safe. And next class, we're going to go a little bit further with this and then start programming where we can take our ideas out of our heads, put them into that computer and get it to do that. And one of the cool things about that diagram that I showed you is that you want to think like, how do hackers get into things and do stuff and make the computer do really cool stuff. And it's mostly comes down to understanding how that computer works. So that's going to be useful for us to get it to do really cool high powered things.